start recording, and I'll try to post it. You're welcome to record too. I'm not going to say anything that'll get me into too much trouble, I think. Yeah, so just to reiterate for the recording, all the quiz solutions, the midterm solutions, and many of the homework solutions are now posted on Canvas, so you can consult with those for help studying. The other thing which I'm going to go through right now and which I also uploaded is, and I did this a few years ago, and I think it's a really good slide deck, is basically my articulating which topics you should be familiar with or strong on coming into the final. Because, we cover a lot of topics, and we cover a lot of details, and some are more important or less important to me than others. Even though in principle it's like study everything, I could test you on anything. But I'll kind of focus in on the main topics, and then after that, if you all want to suggest topics, I can go through topics. I don't see Lillian, but I know that she suggested that we do some transistor review, which I think all of you probably would be cool with. So without further ado, let me just quickly share the overview slides. And again, I posted these on Canvas. So, there we are. Basically, what I did was I just took the heading for every one of my slide decks, and where it has the topics listed, I have in red kind of the things that I would hope you would be able to do. So yeah, let me share this with you. Can you all see this?
Yep.
Awesome. So here, I'll just start from the beginning. This is a cumulative exam, so it's going to test material from both halves of this semester. There will be more content on the newer materials, so that we've kind of, between this and the midterm, we cover the two halves of the course pretty equally. But yeah, let's start at the beginning. So for basic DC circuits, I'd like you to be able to use Ohm's law, know about power dissipation of resistor in series and parallel, be able to do equivalent resistances for parallel and series circuits, understand how those work, understand voltage and current dividers, be able to apply Kirchhoff's laws, and in general, be able to simplify resistive circuits. We do some advanced network theories. I'm probably not going to give you any problems that are going to require quite that level of sophistication, even though those are good to know, and they do actually connect to some interesting mathematics. Yeah, I don't know why there are two slides of this. They look like they're saying basically the same thing. Yeah, okay. So that was a little redundant. For AC circuits, understanding what AC voltage and current are, being able to know how sinusoids work, amplitude, frequency, the relationship between frequency and period, basics of how an oscilloscope works. I could ask you functional questions about, like, what knob would I turn on an oscilloscope or something. Understanding what inductance and capacitance are. And when I say that, we're interested not only in inductive and capacitive reactance, but also inductance itself. I might ask you, what's the inductance or capacitance, the equivalent? And note that the equivalent capacitance is different than the equivalent capacitive reactance, and it even adds differently, because capacitive reactance adds in series and adds as the reciprocals in parallel, whereas capacitance adds linearly in parallel, but as 1 over the sum of the reciprocals in series. So understanding those distinctions is important. Understanding how capacitive and inductive circuits work in AC, phase relationships, that sort of thing. RC and LR circuits and time constants. What happens when you combine capacitors and inductors, like where you can get resonances and things of that sort. Basic filters, low pass and high pass. Yeah, I think that. Oh, and if I didn't say it, like complex numbers, like understanding that relationship So not only magnitude, but phase and how to combine components. Yeah. For the power supplies section, I want you to understand the basics of diodes, like the voltage drop across a diode, resistance, which direction to bias them in, what happens if they're reverse biased. From both the lab and class, how basic rectifier circuits work to convert AC into DC, and have some familiarity with Zener diodes. For the transducers and I/O devices, just know what they are. So like, I don't think I'm going to ask like any rigorous questions like fit the single photoelectron peak of a pulse height distribution for a PMT or anything of that sort. But I might frame the problems in the language of that I'm using a particular transducer or I/O device, and you should know enough of what it is that like you get the problem. But that's all with that. This should be red, but other than that, so bipolar junction transistors, those are the ones we spent the most time on. That's, well, I usually refer to them shortened as bipolar transistors. And then JFETs and MOSFETs, which can be both enhancement and depletion. Know what they are, know what their on and off state is. For example, with BJTs, the default is in the off state unless you put in current through the base, etc. Whereas for JFault is that you can pass current through to apply voltage, and then that stops the current. Understand their schematic symbols. Be able from memory to recognize the difference between an NP, NP, N channel, P channel, etc. I know that it's gonna like for the next kind of like 10 years from now, you're gonna be like, I gotta remember again. But at least like this is the first time I'm making you commit it to me. So yeah. I'm really for this class I don't like to go with formula sheets or open book. I mean, I'm not opposed to those in general. I think with some of the harder courses that have just like tons of stuff like E&M and quantum mechanics and such, it makes sense. But I'll tell you, one of the things is we don't emphasize like internalizing and memorizing things in physics, and honestly, like in the long term of my career, like I wish that there were some things that I internalized better earlier on. But I'm going to ask these questions more like, the number of formulas you need to know is fairly small. You need to functionally understand this stuff. That's really what I like to emphasize. Yeah. So this is also confusing. Why do I have light charged? This is nothing to do with transistors. So biasing BJTs, drawing DC load lines, calculating what the quiescent state is, knowing voltages and currents and those relationships. I'm probably not going to give you the hardest problem imaginable where you need to do systems of equations, but honestly, I think it'd be good to kind of work through how to calculate the steady state of like a divider biasing, and I can talk about that a little bit. But you should know like how the voltages change if you go across different branches and how different things relate to each other. You should be able to identify the three topologies of transistor amplifiers: common emitter, common collector, and common base. You should be able to draw the AC equivalent of a transistor amplifier. You should know basics about current and voltage gain, input and output impedance. At least I would emphasize more for this class the common emitter and common collector, but I'd like you to at least be able to identify common base. This is really weird. Like some of these slides are the same thing, but just slightly different. Oh, this is JFETs. Yeah, okay. So for JFETs, how do you DC bias a JFET? Drawing the transconduction curve, which is kind of the equivalent of the load line. That's that curve that shows you, you start out with this current, and as you increase the base voltage in the right way, it goes to zero. Um, I would say don't think too much about AC analysis of basic transistor amplifiers. I won't give you a problem that if you knew how to do it in BJTs that you wouldn't be able to kind of figure it out for these, but I don't think I'm going to give a problem where I'm going to give you like a transistor amplifier with JFETs. But maybe brush up on that a little. Uh, Also, transconduction curves for MOSFETs, enhancement and depletion mode, know the difference, know like what they do in the on and off state. Like yeah, and yes, that kind of covers transistors. For op amps, how to calculate feedback gains, be able to identify the different kinds of op amp circuits, what they do and how they work, and be able to calculate basic things like gain, et cetera, et cetera. And for digital, I'm not going to beat you guys up too much. If you can deal with binary and do basic logic gate circuits, I think that's the full extent that we're going to do. But I hope you enjoyed and maybe read through again and internalize some of the slides on the subject that we went through the last two classes. And I think that takes us to the end. So, again, the material is going to kind of straddle from slide 6 and 7 on. I might kind of include diodes a little bit in the material that I emphasize more, but the AC and DC stuff will be a little bit less emphasized on this, but there will be problems. So make sure that if you got things wrong on the midterm, that you know how to not get them wrong for the final. So that's what I have on sort of what the final is going to cover. Any questions or comments? Further questions or comments? Okay, I'll take that silence as you guys are ready to kick butt on Monday. No, just well, no, I take it that way, but that doesn't mean we can't go on. I think what I'll do for starters is pull up my slides on transistors because I think that's where I'll go through the op amps too, but transistors and op amps are where I think we're gonna dig in the most like meaty problem solving stuff. So you all can ask some questions and we can go through. Yeah, so let's see. Lecture 6. Don't worry, everyone. The semester's almost over. We're close. Uh, you get a lot out of your way on Monday. That's on the bright side. Okay. So, again, understand the anatomy of a transistor, uh, how depletion zones work. Remember, I posted those additional slides and I forgot to post the links. But if you go on my YouTube channel, I think I've posted at least one video from my YouTube channel, and I think some of you know what it is. If I don't get a chance to post them, I do have video recordings of Return of the FET and that is MOSFET and Revenge of the Fat or something, whatever the JFET one was, and the diode one where I really explained depletion zones in depth. Understand basically how transistors function. Understand the schematics for both NPN and PNP, be able to interpret them, and know how to bias them. So, one of the things that came up yesterday is how it works with the voltage. And I think in the quiz, let me see. Oh, I've got my solutions to the quiz in front of me. Uh, so in the quiz, what did I ask for? I gave you the voltage at the emitter. I said that the voltage at the emitter was 5 volts, and therefore, what is the voltage at the base? And is that right? No, 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 no. I'm sorry. I got it backwards. I realized that the sign wouldn't work out if I did this. I gave you the voltage at the base. I said that it was 5 volts. Then I asked, what's the voltage at the emitter? Now you'll notice, and in the quiz, it was an NPN transistor. And you'll note that the arrow is pointing this way, which means that the junction from the base to the emitter acts like a diode where, this is the anode, and this part is the anode, and the emitter is the cathode. And when you cross a diode, the diode's internal field is like an oppositional field. So whatever voltage I'm applying at the base goes down by 0.7. So the voltage at the emitter is 4.3. Now, what I think confused a lot of you is that in previous problems, including ones that I did that day, we went the other way. We said the voltage at the emitter is blank. What is the voltage at the base? And for that, you add 0.7. Now, an interesting thing to note is that, in a sense, it's the same exact thing for a PNP. The difference, though, is so if you start at the emitter and then you go, or sorry, if you start at the base and go to the emitter, you're subtracting 0.7 volts, which makes the voltage that was at the base a smaller positive number. Here, you're adding 0.7 volts, but you're adding 0.7 volts to a negative voltage. So the effect is a magnitude reduction. You have a less negative voltage on the other side. And similarly, if you go from the emitter to the base, the magnitude goes up in both cases. Here, it's more positive. Here, it's more negative. So it's kind of a similar concept, but you need to get that going. It's critical, though, when you're trying to understand the biasing of a transistor, that you recognize this relationship, because this relationship is pinned down. And it leads to these confusing, like almost like time loops in time travel movies, this sort of feedbacky situation where, the current going through the emitter collector path depends on the current going through the base, and the voltages on both depend on the currents, but the voltages between the base and the emitter, you can think of base as cause and emitter collector as effect, but some of but there's this weird tie-in that the base is also causally related to the emitter. So I'll talk through that in the next slide, but you just have to recognize that the relationship right at the base and right at the emitter has to have that 0.7 volt relationship. And so whatever the final steady state behavior of that transistor is, it has to be such that that relationship is maintained. Okay. Um, the other important thing to remember whenever we're talking about biasing a transistor is that if we're applying a voltage across the emitter collector, so it's usually called either VCC or VEE, or maybe we'll have both. We'll have a positive voltage and a negative voltage and some voltage difference. The total voltage across the transistor, what we call VCE, is going to be the total voltage difference applied across it minus the voltage drops of whatever resistors are in that path. And it's on both sides of the transistors. So let me skip to this slide. Here we're applying 15 volts. Let me quiz you guys in the chat. Well, let me pull up the chat so I can see. What is the largest voltage that can be applied across the transistor? Oh, 15 volts. That is correct. We can't we can't make we can't make the voltage across the transistor bigger than the applied voltage. No, somebody else, because this isn't a game show, can somebody else chime in with what is the circumstance? Sorry, Emily. Um, by the way, I had a friend who like I would watch Jeopardy with when I was actually you guys' age or 1 year young, 2 years younger when I was a sophomore. This guy, every single question he would get it right before anybody could answer, and to this day I still don't understand why he wasn't on Jeopardy and became a millionaire. But anyway, and it's not just knowing, it's being able to buzz in super fast. Anyway, the what is the condition under which what causes the condition under which the voltage across the transistor VCE is 15 volts? Zero current to the base. That is correct. So if you're not applying any current to the base, then there won't be any current going across the collector emitter, which means that there will be no voltage drop across RC or RE, and therefore all of the voltage of that 15 volts is across the transistor. So zero current to the base is your one endpoint of your of your load line. It's the point where you have minimum current but maximum voltage. After that, any current you apply to the base is going to increase the current going through VCE. Now, this is another one of the relationships that you have that has to be true, is that ICE, IC or IE, I should say, those are two separate currents, have to be equal to beta times the base current, IB. And in fact, it's technically IE, the emitter current equals beta times IB. Technically, IE, the emitter current, is 1 plus beta times IB, because the emitter has the current that's going, or I think I said it backwards. The collector has beta times the base current. The emitter has beta plus 1 times the base current because it's seeing the collector, it's driving the current through the collector, and it's also receiving the current from the base. And those add. But of course, if the gain is huge, like 1,000, then 1,000 plus 1 is not that different from 1,000. You know, uh, 1 plus big number equals big number. So you can approximate, as far as I'm concerned, IC equals IE in any problem I give you, and it's a very useful approximation. Um, the but anyway, uh, as more current flows from the emitter to the collector, then we get a voltage drop. We get a voltage drop on both sides of the resistor. On the emitter end, when current is flowing through here, instead of this side being 0, now it's going to be IRE. Okay, so the voltage right here is going to be equal to IERE or ICRE. And the voltage here is going to be 15 minus ICRC. And so the total voltage across this is going to be 15 minus ICRC minus ICRE. Or you could write it as IC times the sum of these two resistances. And in the extreme case, as we push more base current through, the voltage drop across the resistors is going to increase until what point? What's going to be the breaking point? It'll actually be a little bit before that, but for all intents and purposes, we can just take it to that extreme. Somebody? It's a little complicated to type in chat. Okay, this is really dramatic. Oh, saturation. Oh, sorry, I just gave it away. Um, what is driving the saturation though? What's true about the voltage drops across the two resistors at saturation? Yeah, all the voltage drop is across the resistors, and so none of the voltage drop is across the transistor. So in fact, the transistor is going to stop working a little bit before that point, because you actually do, if you remember, you do need to have a little bit of voltage across the transistor to even get to your effective um, uh, collector current. But for the most part, that's certainly like a good approximation of the endpoint that you can reach. And so that gives you, of course, your uh, your your load line, with the one extreme case being where the collector current is 0 because the base current is 0, and the voltage across the transistor is 15 volts, and the case where the current is the voltage divided by RC RE plus RE, because the voltage drop is across all of just those, and the voltage across CE is 0, and so those are your two extremes, and those are the edges of your operation. And why are we biasing a transistor in the first place? Well, we're biasing it because ultimately we want to use it as an amplifier. And we want to use it as an amplifier that amplifies upswings and downswings. But of course, if we are at this edge, we can maybe get a downswing, but we can't get an upswing. And similarly, at this edge, we can get an upswing, but not a downswing. And so what we usually want to do is we want to adjust the steady state operation of the transistor, the Q point, to be somewhere between these two ends. And, something approximating the middle is good enough. If I don't specify and you get anywhere kind of in the middle of this, you're in okay shape. And there are different ways of biasing it. The base bias is the simplest. The more complicated one, but very useful one, is the voltage divider bias. And I'll remind you folks that the way that the voltage divider bias works, to some approximation, you can just take the resistors and treat them in isolation and say I've got 15 volts split between 18 kiloohms and 3.6 kiloohms, and then figure out what this voltage is. But that's assuming that all of the current is going through these two resistors. The fact that a little bit of current is going into the base does actually change the balance a little bit. This voltage drop, I believe, is bigger than this voltage drop in that case. And you could do a proper multi-equation calculation of the steady state in that case. I would really encourage you to try to do like one calculation like that. I don't think I'm going to ask you to do one from scratch on the exam, but I might ask you to do part of the calculation. And the more you understand how to set it up, the better. And again, just walking you through calculating the steady state of this, we know that there's some current, ICE, that's going to be going through this. And ICE times RE, or sorry, IC, I should say. IC times RE is going to tell us the voltage right here, VE, because we're 0, and then go across a voltage drop, we're at ICRE. Okay. Then when we want to work backwards, when we go from the emitter to the base, we add 0.5 to that, and that tells us the voltage right here. And then because we now know the voltage here and we know this voltage, we could figure out the resistor values that we need to get there, for example. And then we also can figure this out, because whatever that IC is, ICRC plus ICRE subtracted from 15 volts is going to be the voltage drop across our capacitor, etc. So, knowing all these, and again, the relationship between whatever IB is, IB times beta is going to give us IC. So those are the relationships that pin down how the DC part of this circuit works. And now I think we can talk a little bit about the AC. You'll notice that for the DC biasing, we do have a resistor down here. But this is actually a common emitter, meaning the emitter is tied to ground, but it's AC tied to ground. So that's what this bypass capacitor is for. The AC, as far as the AC signal is concerned, the emitter is tied to ground. And where do we take the signal from in the amplifier if it's a common emitter? That's a question to you guys. Where do we pick off the output of this transistor amplifier if it's a common emitter, if the emitter is tied to common ground, AC tied? Correct, the collector. And similarly, if it's a common collector, the signal is taken from the emitter. And remember, a common collector has the second name, which makes it confusing that it is a collector or an emitter follower. Yeah, I think I've thought of that before. I'm not sure, but I do sing TNT with my kids. Um, Lots of AC/DC references seem to pop up in my career. I guess, well, if you teach electronics, AC/DC. Fun fact about the band AC/DC, because I 1 year lived with I had an Australian room, apartment mate. Um, in Australia, and this is, I mean, it might also be New Zealand, I don't know, but it's unique to that part of the world. AC/DC is referred to as akadaka. Like they don't say AC/DC, they will say akadaka and expect you to know what they're talking about. Um, and if you ever need to figure out if someone's Australian, as if that's hard to do, if they say akadaka, where does the A come from? In what? In AC/DC? Or are we back on topic? Oh, yeah, they just, they gotta add Australians. There's no rational explanation for it. You live in a country that has like snakes that can eat babies and things like you just you're weird. I really want to go someday. Anyway, let's get back on task. Um, so, in a sense, when you're dealing with transistor amplifiers, it's a similar phenomenon with diodes of where a small swing in voltage across a diode leads to a large swing in current. And if you have a resistor on that current, the resistor voltage will be large. And that's kind of what's going on here. This is your diode is your emitter collector region. And in the case of a common emitter, you get very large voltage gain, um, where the small current through here, or the small voltage difference or whatever, which translates to a small current through here, makes a large current through here that once seen through this transistor or resistor turns into a large voltage swing. And you'll notice that if I were to take this point off and do a DC, when the base current swings up, this current actually swings down from whatever it was with respect to 15. And when the base current swings down, then I'm subtracting less off of 15, so this voltage swings up. So there's a sign flip to note there. And there's also, by the way, if I'm picking this signal off with a DC probe, it's also going to have an offset to it. It's going to be a fluctuation around the quiescent voltage of 7.5. But very often when people make these transistor amplifiers, they'll put a capacitor on the output. They'll capacitively couple it, which will give you the same amplified signal, but centered at 0, which is probably what you want. It's still phase shifted, though, in that case. If you want to do the AC equivalent circuit, which is something I could potentially ask for, remember that all voltages that are DC voltages are equivalent to ground as far as AC is concerned. So this is ground, this is ground, this is ground. All capacitors are wires, so this is a wire and this is a wire. And we'll get what to do with the transistor in a second. But one important thing to point out is that R2 is tied to ground and R1 is also tied to ground from an AC standpoint. So these are actually in parallel to each other from the standpoint of the AC circuit. Now, the way to draw out a transistor in its simplified form is basically to have a current source where the current going through this path is equal to the base current times beta, and then that current is being driven across this resistor. Um, on slide 39, are the voltage drops across the load opposite to, are the voltage drops across the resistor opposite the transistor? Yeah. So you're asking, are the voltage drops across the transistor opposite to the load? That's a good question. I don't have a pre-memorized answer to that, but we can work through it. So let's say that the base current swings up. So we're applying more base current. That means that we're applying more current through this path, which means that the voltage across the transistor necessarily is going to go down. It also, though, means that the voltage on the output is going to go down, i.e., the voltage across the output is going to start at the quiescence voltage of 7.5, but now it's, instead of being 15 minus the steady state current, it's going to be 15 minus the steady state current plus, which is more subtraction. And so it's going to go down. Or wait, oh no no no. So you're uh, thought I said it right. Let me make sure I'm saying this right. So uh, the current through here is increasing. So the current through here is increasing, which means that this voltage drop is going to be larger, which means that the value of the voltage here is going to be even smaller than it was. So instead of 15 minus 7.5, it might be 15 minus 7.8 or something. And so it's going to go down when this is going up. But that it's going to be in phase with what the voltage difference across the transistor is, because the voltage difference across the transistor is also inverted with respect to the source. When the source is going up, that means that it's pushing through more current, which means that the current through the emitter current or the collector current is going to go up, which means that the voltage across the transistor is going to go down. So the sign of the change of the differential voltage across the transistor and the absolute magnitude of the voltage at the point of the collector are going to be going the same way. Did that answer your question, Dan? Cool, cool. Yeah, it's good to go through these. So yeah, that's the basic idea. And so when you draw the AC equivalent of this whole mess, what you get is you get these two resistors in parallel. And oh wait, yeah, this is common emitter. Um, and you have this circuit right here, but this resistance is very small, and this is like an AC short. And when you're calculating the gain, uh, you have the situation where the input voltage is equal to the voltage across here, which in AC is just the voltage across this tiny resistor, and so we can write that as ICRE. And when we work everything out and we get the ratio of V out to V in, I believe I posted where I work out these, but it's definitely worked out in the textbook. You get that V out to V in is equal to the ratio of this resistance. Well, usually, let me be a little bit clear. This is important to clarify. You'll notice that in this formula we wrote lowercase rl. What do we mean by lowercase rl? What we mean by lowercase rl is we mean the parallel combination, because these are parallel to each other from an AC standpoint, of the collector resistor and the load resistor together. So if I do the parallel combination of these two resistances, that's R sub L, and that's the total resistance that is seen on the upper half of the transistor circuit. And on the lower half, it's lowercase r sub e with an apostrophe over it, which is the internal resistance of the diode, and it's that ratio that gives you your gain. Okay. Now, sometimes you might want to actually swamp this transistor amplifier. And what that means is putting in a small resistance that's larger than the diode resistance. You'll notice that this is a swamped one because they don't have an apostrophe, and this is 60 ohms. It's not, here it was like 3.33 and there's an apostrophe. This is the diode resistor alone. This is the diode resistor in series with some small resistance. And it's a different one than this because this one is being bypassed. But if we had one that wasn't being bypassed, but was like 60 ohms that we combine with RE, that would be a swamped amplifier. It reduces the gain because now the ratio of RL is to 60 ohms instead of 3 ohms. So that's the gain. And that makes it a smaller gain, but it's more stable because it's driven more by a resistor than by a very tiny nonlinear diode in a solid state device that's probably temperature dependent and varies from transistor to transistor. I can buy a very precise, well-spec'd resistor for cheap that I can use to kind of set a very stable voltage point. And that's why you might want to swamp it. But in general, the gain overall is the ratio of all of the AC resistances above to all the AC resistances below, whether that's just RE prime, which is like 3 ohm, or RE plus some swamp resistor, like in this case 60 ohm. This one does not count though because it's got a capacitor across it. It only is useful for the DC biasing. Does that make sense, folks? Cool. I am going to have to go in about 13 minutes or so, but I think this is a good review of transistors, and we can talk a little bit about the other transistor kinds. Common collector, where is the signal taken from? Well, it says it here. If it's a common collector, the signal is taken from the emitter. You'll notice that the feature of the common collector is the collector is directly attached to the voltage source, which also, by the way, means that that it's tied to ground, hence common collector. The collector is tied to our AC reference. One of the things you'll notice is that whatever we put as our input, when it swings up, the common collector swings up. So it's actually in phase. And the really key thing is that when we do the AC equivalent circuit, this time our load is in series with R sub E, and the input voltage is across the two of them. So this is a voltage divider, and this is my output. So my output is how the voltage is divided between this tiny resistor and a much bigger resistor. And so if you have big plus a little number divided by a big number, you're going to get something that's very close to 1. And so the voltage coming out is going to be very close to the voltage going in. Not exactly. It will be slightly smaller, but it's close to 1. And this was on the quiz. An emitter follower, or a common collector, has a unity voltage gain. It has a very large current gain. The amount of current being pushed by this source is very small compared to the current being pushed through the output, but the voltage is close to 1. So that's a key feature of these. And I leave it to you to kind of review in the textbook input and output impedances, because I'd like to go on. But that's the basics. And remember, a common base, you have the base tied to ground. And I'm not going to really ask technical functional questions about these, but it's possible that I could have a picture of a common base amplifier and ask you, what kind of amplifier is this? And if you say transistor amplifier, I'm not only going to give you 0 points, I'm going to take them. No, I won't be that mean, but I'll feel like taking away points. So yeah, so let's go back to JFETs. If you remember, JFETs are field effect transistors, and they are basically transistors where you have a channel, and the channel allows current to flow through it in the default state. It has some what we call transconductance to it, 1 over the resistance or the resistivity. And that depends on how many charge carriers are in the channel. But if you apply a voltage that reverse biases the diode junction between the gate and the source, then you end up expanding the depletion zone in a way that can choke off the current. So with a JFET, you have nowhere to go but down. You start out with maximum current, and then you can reduce it to zero. So what we call the transconductance curve looks like this, where at zero bias voltage, we're at 10 milliamp, and at -4 bias voltage, we hit zero. That's what we call VGS off. Okay. And that depends on the particular choice of material, but the operative is that if you think of the gate source as a diode, PN, the condition under which you will choke off the current is where you are reverse biasing the diode, because as you recall, reverse biasing a diode expands the depletion zone. So to forward bias a PN junction with a diode, you would apply positive to P, and you can see here we're applying negative to P, and positive, or at least less negative, to the source. And that's the key to how to bias these. You can make them, I will just say, in transistor amplifiers that behave very similarly to the analogous transistor amplifiers in BJT transistors, with, of course, some caveats. For example, in this case, when the voltage is going up, we are reducing the current through this path. Whereas in a BJT, if the voltage over here is going up, the current through the base is going up, which increases the current, which drops the voltage. So, there are some differences, but there's a lot of similarities. For the voltage divider bias, it's easier because you can assume no current going through here. And therefore, the voltage is set purely by this voltage divider because there's no current. This is one of the advantages of field effect transistors, is you're actuating the transistor not by pushing a current through it. Even if it's a small current, it's still a current. Here, it's a voltage, it's a field that you're using, and so you don't need to push any current through. Now, because field effect transistors have the gate in physical contact with the drain, as with all diodes, there is a slight leakage current. So it's not totally technically true that there's no current, but like however small it is in a BJT, it is much smaller for a JFET, and that's the key thing to bear in mind. So with MOSFETs, it's a little bit confusing because now the name of the game is that you are going to apply a voltage to a gate that is completely decoupled from the sort of channel material, because there is an oxide layer in between that serves as an insulating layer, hence metal oxide in the term MOSFET. In this case, you're not reverse biasing a diode. Rather, you're applying a voltage to the gate that attracts more charge carriers into the channel, making the channel more effectively conductive. And so, for example, this is a P channel. So it's got positive charge carriers. If I apply a negative voltage here, it's going to induce more positive charge carriers to build up in the P region, thereby enhancing the transconductivity of this. And if I apply a positive voltage, it's going to push out some of the free positive charges, making this have less charge carriers, which decreases the transconductance. And so unlike a JFET, you go both ways. Without any gate voltage, this kind of MOSFET will allow some current to pass through, but I can either make it more current or I can decrease it. So this is a P-channel depletion type. So this is a D MOSFET, it's called, a depletion type, because you can both enhance and deplete. The other kind of MOSFET is one where your channel, in this case an N channel, is cut off by the P-type material. And that means that there is zero current through this if it's unbiased. So if you don't bias it at all, its default state is off. And it's a little bit counterintuitive that this is called an enhancement MOSFET. But the way I like to think about it is it's an enhancement MOSFET because it's got nowhere to go but up. It's already at zero. So I can't make it have less current. I can only enhance it. And I do that again by inducing charge. In this case, I want to apply a positive charge that encourages more negative charge carriers to build up here, creating a conductive path that is sort of uh, making it through or tunneling its way through the P material. It's sort of a weird way to think about it. I'll point you guys to the fact that I do have those videos on my YouTube channel. I'll try to remember to post them on Canvas, but they are out there, and that's a useful thing to look at. So yeah, that's MOSFETs. Uh, don't worry about relays. We didn't talk about them much this year in class. They're electromechanical magnets. Pull it into the off state or it springs back into the on state, and they're fun. And I'm sorry you guys got to miss out on the joy of like making one of these things hum at like 2000 hertz and making the sounds, but next time. So yeah, that kind of covers the transistor stuff. Any questions or comments? Let me.
Is the exam going to be fun?
Of course, is
Wow.
what do you, this is everything that we're doing in this class is fun. I'm not going to promise that actually because I've learned over the years that fun is a highly subjective term, even among people who generally are inclined to find stuff like this fun. There can be some variation. It also depends on context and time of day. I think electronics is really fun. Am I having fun with electronics in my experiment now? No. So it's a spectrum. But on the other hand, I'm going in person to my experiment next week, and even though I've got a lot of problems to solve, it's going to be fun again because I get to like actually roll my sleeves up and use an O-scope like I've been making you all do. So fun is relative. I'm gonna try and make it not painful. I'm gonna try and make it. I mean, if you folks enjoyed the midterm, if you found it interesting and fun for a midterm, I think you'll be happy with this. I'm not gonna try and beat you up, but that's also a subjective thing because you give an exam and I I've
Yeah.
never like been in a situation where like the student interpretation of the exam was how I expected it. Sometimes I would give one that I thought was rough, and the students were like, "Oh, that was great. It was easy," or like blah blah blah. Yeah. Anyway, enough philosophizing about fun. Let's just quickly look at op amps. Like I said, for digital, I want you guys to understand Boolean gates. If I put a few Boolean gates together, can you make a truth table? Um, can you identify those symbols? And can you do binary? And I'm going to maybe throw in there, can you do hexadecimal numbers? That would be a useful first skill. I would say in the long run in your career, um, it would be, like when you have an opportunity to formally do more digital circuitry than we were able to cover in this class, it's really obviously useful. So everything I've taught you is useful. It's just there's a lot of useful stuff to have to teach. Yeah, I mean, take it. It's good stuff. I really only have a couple more minutes, unfortunately, but I think that I can just quickly point you to what I see as some of the essentials of the op amp stuff. Give me one quick second. Operational amplifiers. Can you guys see that? So know what one is, know what the diagrams look like. You'll notice that on multisim, you could select a 3-pin or 5-pin. What that means is 3-pin means you're going to pretend that somebody else figured out how to power it, but that it's being properly powered and you're only worrying about the 2 inputs and the 1 output. 5-pin means like you're actually worried, like in the multi-sim circuit, you're actually going to worry about how to apply power to this, and you're going to design the power bus. And so the 2 other pins are your plus minus. You'll also note that in some op-amp chips, you also need to tie a pin to ground, et cetera, et cetera. Know like the key properties of op-amps, know how to compute gains. So, know that an op-amp amplifies a small differential signal. The differential is an important piece, and it amplifies it by some huge gain that I theoretically need to specify what the open loop gain is. Know also that you can combine op amps into feedback loops, and I need you guys to be able to recognize those feedback loops and know sort of how to calculate them. And what sets the gain values, for example, like the ratios of the resistances. You don't really need to know this, but it is good to understand a differential analysis of how an op amp works. Know things about, like, for example, that there is this speed rise time effect. I don't think I'm going to ask you anything calculation wise, but this something that I'd like you to know that I could do something with on the exam. Again, like I said, with the different kinds of feedbacks, and remember, like, there are 2 different kinds of negative feedback. You can get unity gain. I'd like you to know the different types of op-amp circuits, like voltage summers and what those do, summing amplifiers, like a mixer board. Let's see, filters. You guys should definitely know how filters work with op amps. If you do the multi-sim exercise, that'll help a little bit, at least with one type of amplify of uh, filter. Then, like, the other kinds to know are things like the voltage to current converter, current to voltage converter, like know what running in saturation looks like, using op amps as rectifiers. I think that's mainly it for op amps. But all those things I just said, and again with digital, at least be able to do truth tables and recognize the logical primitives. And of course, be aware that those logical primitives themselves are not electronic components. They are effective logical components that take high and low voltages and output a high or low voltage according to some convention. They're made by an assemblage of transistors and diodes. It's helpful. I would say that I would like you, especially looking at, for example, the midterm exam, in light of what we've done with digital electronics, try to kind of understand how setting things to high and low with diodes and or transistors might produce logic gates. I'm not going to ask you hard questions on that, but I really think that that's something I'd like you to know as a takeaway, because an OR gate, like I said, is not a fundamental electronic component. It's actually an emergent property of an assemblage of transistors or diodes. But we, reduce it to this unit cell thing for the purpose of planning out how logic works. I don't think I'm going to test you on sequential logic, but that's super fun stuff, and so definitely, like, watch some videos on it and stuff. Be careful. One video I was looking at on YouTube, the narrator flipped the inverting and non-inverting output, and, like, I was racking my brain because it didn't make any sense. And then I looked at the YouTube comments, and it was just like hundreds of comments of people being like, "Yo, you flipped the outputs. You flipped the outputs, going all the way down." So be a little bit careful with the YouTube. But that's it. I really got to run, but are there any other urgent questions? If not, feel free to send me an email. I will be trying to check. I won't check my email tomorrow. It'll be on again, off again over the weekend, but I will try to check it in case anything urgent comes up. And as I mentioned, I'm not physically going to be at the exam. Eric is going to be proctoring for me, but I will be on call and text. So like if you have a question for him that he doesn't know the answer to, like why the heck did I do this, or what's beta supposed to be, or you didn't label this, but I will be available to answer questions. And I, again, really enjoyed having you all in class. It was a lot of fun, and I wish you all luck in the future and even spring semester. If you have any career or electronics questions for me, feel free to stop by my office.
Thank you. It's fun class.
Thanks. All right, I'm gonna drop off because I have another call, but good luck, and I'll talk to you guys again soon, hopefully.